let's get started. So it's my pleasure to introduce ZX Shen, who's going to be talking about the VUV and soft X-ray science at SSRL. ZX, I'm not going to be as good as Paul with the introductions. ZX is a professor of applied physics and physics. I put applied physics first because that was our initial department for both of us. And he was a student. He graduated, if I remember right, 1989, and started doing, kind of put together the system on Beamline 5, which was the undulator, using the first undulator, and put together that system with morphed into a fancier undulator, and then he made the ultra high vacuum system work at high resolution, which was one of the highest resolutions at the time for doing angle resolved photoemission. And from there, I'll let him tell you the rest of the story.
Thank you.
ZX.
Thank you very much. It's a great honor to be here to give this talk, especially following Audie and Keith. As many of you probably know that Audie was the one who brought me to Stanford some 30, almost 40 years ago. So that's where I started my career. I've been told to talk about the VUV and the soft X-ray material science. And as you can see that I get a lot of input from Piero, Ingolf, Donghui Lu, and Makoto Hashimoto. Okay. So these are the few topics I would like to touch on. I want to reflect also in this space, the pioneering days. Then I want to tell you a little bit about the case study of our work using angle resolved photoemission to study quantum materials. Then I will also say a few words about how important it is to build a partnership and an ecosystem bridging the university and the laboratory. And at the end, since this is one of the occasions, we can see a few reflections. So I actually took this slide from Piero. So that's the historical context of a motivation. And basically, we'll try to build a high energy storage ring and to operate at 72. Will be used to study uncharted territory in particle physics, as history has shown led to 3 Nobel Prizes. And then the question was, could this source be of high intensity X-ray being used to do something? Piero's original version was do something useful. You know, Piero is extremely humble. So I changed that to doing something novel from the materials and chemistry and laboratory. Okay, so the last line was also Piero's. He said something useful again, and you can see that actually it's not something useful, it's something transformative. So those are the pioneering days, as touched earlier, but earlier talk, especially that of Audie, I think inspired by a note from Hegstrom, Spicer wrote to Panofsky in 1968. That was in the planning phase of the sphere, saying that leave a port for synchrotron radiation. Then a proposal led by Seb, Bill, and Audie get the project started. And that's the picture of Seb Doniak, Audie Bienenstock, and Herman Winnick at the old 120 building. And the lower one is the picture of Spicer and the Lindau. Okay. So this is the first experiment. That's Piero and Ingolf in their early days. As Ingolf was a postdoc and Piero was a graduate student. And that white-looking alcove was where the experimental was set up. And inside this is the instrument, and you can see the window. That's the brilliant window. That was the handwritten written note by Ingolf on the notebook of Piero's experimental notebook. So that's the first light from the spear range. Okay. These are the two first reports in 1972. To the left is the photoemission spectra, comes from gold 4F, okay, and to the right is the XF data of 19. And noted that for those of you who are familiar with photoemission, hard X-ray is not a good place to do photoemission, but it's the only place you can bring beamline out. Even with not optimal condition, the spectra from photoemission already shows that this is going to be a field with tremendous impact. Okay, so that's already there, and that's the 74 Nature paper. On the right is, I believe, the Peter Eisenberg's handwriting is to say that it takes 20 minutes to collect the data of same quality as that of an X-ray tube for 10 days, and that's. So I want you to note that the date was 1974. Okay, this was actually a very critical time also for high energy physics, already reflected to in this. Those data were taken with one shift of beam time, I think. Okay. Those are very happy times. You can see that everyone, as look at Piero, how happy he was. Okay. And Ingolf, when he was not stealing on the equipment, he was also happily, bathing the sun. And so this also, it's a picture reflecting the collaboration between Berkeley, LBNL, and SLAC. There was a very, very good spirit of collaboration. And in this picture, there's also Zahir Hossein and Chuck Fadley. Okay. And Zahir and I later form a very strong partnership for collaboration, again, across the two laboratories. This tradition of collaboration between the national labs really has impact and benefited both. Sometimes there are competitions, but overall, this collaboration makes everybody win. And again, those are the early days. That's the semiconductors and the metal surfaces studies. And to the left with the Stanford group led by Piero. To the right, I think Joe at the time was still at LBNL, working on the angle resolve photoemission data. And you can see again, the two laboratories also working together. I was beginning to sense early days. There were also, of course, competition for beam time. That's the way things go. But as a whole, I think each side helped each other. So I came via Artie. Then I joined the group of Spicer and Lindahl. I was a graduate student number 36 on the list. And Ingolf signed me to work with Jim Allen. At the time, he was working at Xerox Palo Alto. And this also says about the location of this place. We were embedded in a very, very rich, science-rich environment. And Jim was working on oxide before the high TC comes. So he was working on nickel oxide with the famous paper with Zavatsky. That's the scheme called the Zalman-Zavatsky-Allen scheme. So he was very knowledgeable. I learned enormous amount of the many-body physics from him. And Bill and Ingolf was extremely nurturing advisors of that. So that's my first paper, actually, with Jim, Bill, and Ingolf, and with samples coming from Brian Maple, also Ted Ball. Again, is a connection with the university. So I was hired at 92 as an assistant professor, almost 30-some years ago. And BES has supported me continuously. personified by Jerry Smith, Bill Osterheis, Helen Kirch. Helen, is so great to have you here, and also Lane Wilson. And Dan Dessau joined me as the first postdoc, and David King as the first graduate student. So now I'm going to say a few words about how we build on what the foundation Bill, Ingolf, and Piero, and others had built at SSRL and taking it to a different direction. Okay. So my scientific interest really is mostly on the scientific foundation for the next generation quantum materials. To the left are the two Nobel Prizes for semiconductors. And that, of course, the first generation of quantum theory have made tremendous impact of first generation quantum technology as represented by silicon-based semiconductors. In many ways, you can say that we have optimized one property of one material, the conductivity of silicon that transformed our life. Okay. To the right is a representation why that class of quantum theory doesn't work. And as reminded by the dramatic failure, discovery of the high temperature superconductors. In this case, the silicon class theory will predict this to be a very good insulator. Okay. And that's where things started. And the goal was try to make precision measurements of the key parameters, try to guide the development of theory. You may ask why this is so hard. Okay. One way to think about it in this era is to think about all the quantum materials are doing their own quantum computing in the system. The Hilbert space are tremendous. Okay, it's extremely difficult. Whatever the theory we will do is by definition classical. So you try to do a classical mimicking of what a quantum system will do. And that's why it is challenging. In systems which are simpler, you are way into a stable phase, like silicon. That classical sort of first generation classical description was easy. But in systems where the subtleties lead to dramatic effects, such as high temperature superconductivity, this simple classical calculation was not sufficient because the Hilbert space is so big. I mean, give one example, the simplest model going beyond the silicon class theory, the Hubble model, being around for 5 decades, and yet had not been solved. Has it been solved with 32 atoms at that small space with the most powerful computer today? So that's the intellectual challenge why we are doing what we are doing. Okay, so angle resolve automation, and it is so important that to build a system where you have an ecosystem that you have instrumentation, you have materials, you have data processing, and also the scientific agenda, okay, intellectual agenda. As you will hear again and again, how important it is that to have the right ecosystem. The success of SSRL can also be attributed to it was embedded in a very rich science and a problem ecosystem. To the left are the two people who really contributed to the progress. That's Donghui Liu and Makoto Hashimoto. And I also show a picture of the beam line being used. Okay. So that's sort of the timeline of that before 99. And that was the beam line 5.3. And it's a VSW analyzer. Okay. And at 2000, we upgraded it to a normal incident monochromator with the modern Sienta analyzer. And in 2017, and we upgraded again. Throughout this way, I think the BES really supported us in a sustained way. Without that long-term sustained support, this program would not have been possible. I want to also make a note that the innovation of the technique combined with science, that is critical. In 1991, we made a one-dimensional multi-channel detection. That a factor of 10 improvement made a critical difference in the early experiment. Just as a statistics, the beamline 5 of SSRL produced about 30% of the synchrotron-based papers in high-impact journals. And that's just one beamline. This is equivalent to all the beamlines in Europe and Asia combined, the same number of the papers. So let me give a couple examples of that. In this sort of experiment, for this audience, we use the photoelectric effect, use synchrotron light source, eject electrons from the surface, then you measure the energy and the momentum of those electrons. To the right-hand side are the citations of the papers over the period of time. And you can see that there's a very dramatic growth of that. One of the important milestone or inflection point was the discovery of the D-wave superconducting gap structure in the early 90s. And for a superconductor to have its normal properties, you need to take the two electrons and make them form a pair. How they pair will tell you a lot about the mechanism of these systems together. In conventional superconductors, you can think about them being paired symmetrically, so-called S-wave, means that the superconducting gap should have been a constant, okay? And in the novel superconductors, they turned out it pairs asymmetrically in the D-wave channel. Okay. This detection shows that the angle resolved photo emission can be a quantitative tool to answer a question whose answer is a priori unknown. As I said, the challenge was that the quantum materials were doing its quantum computing, and we're trying to make a classical projection of it. And this is very clearly, we say it's going to be projected into this state. And that success is telling you this experiment could be applied to many other quantum materials. And then you can see the rapid rise of the citations of this because this technique is being applied to many other materials, including them in the topological insulators of the discovery of that. Okay. Now I'm going to show how the technique advance made a difference for these two discoveries. That was the earlier paper, okay, of the D-wave gap structure. We did the experiment at SSRL with the samples from Aaron Kapitunik's group and with a lot of in-series insights from Savdonek. Okay. And you can see that at the time, we can only take 4 spectra because your surface need to be clean. Okay, so we have about 10 hours before the surface sort of have other things condensed. So that factor of 10 improvement of detector made critical difference because you wouldn't have the signal to noise. So if you look at the spectra taken at point B, okay, at point B, you can see that the red and the blue data are more or less the same. There's no difference above and below the transition temperature. But when you look at point A, you can see a clear difference between blue and red data. Okay, that was the first indication that we may have an asymmetric pairing because it's an angular dependence. And the way asymmetry works turned out is very consistent with pairing. Okay, that's 30 years ago, and 10 years later, now you can make a very detailed map, and you can see that the solid curve in the data point, and you can see is the series of the D-wave pairing structure and the data point. is very consistent. Okay, as I said, if this will be a S wave, they should have been a constant across with respect to angle. This was good. However, if you're interested in some of the subtle quantum physics, such as the possibility of existing of a quantum phase transition and a quantum critical point, then you really need to look carefully where the gap is zero, the order parameter changing sign. And you can see that if you really look the data point in the circle, and you see that's not enough to study the subtleties. And another 10 years passed, and that's the experiment. That's the thesis work of Innovishik. And you can see that, as you can see, for an asymmetry D-wave superconductor, the most sensitive parameter is the node of the D-wave, where it goes to zero, how it goes to zero. It turns out that she finds that for these 4 samples, even though the superconducting transition temperature changes dramatically from 40 Kelvin to 90 Kelvin, the node doesn't change at all. The 4 data look the slope is the same. However, at a critical doping, you suddenly see changes of that. Okay, so that's a very important progress. So let me give you another example of the discovery of the topological incident. Because we are so shaped by the success of the description of the quantum of silicon class of material. So we are very used to thinking about the energy levels and band structure. It was the realization that, in fact, when you solve the Schrodinger equation, there is eigenvalues, the energy spectrum, and there is also the wave function. And turns out the wave function was very important, gave you the curvatures which are important to the properties and even a topological properties of protection. And it was theoretically predicted to have that if you realize the importance of wave function. So those are the pioneering papers, and it shows that you can have a bulk band gap with a band inversion. Then you have R number of robust, the rock-like cones. And if you break the time reversal symmetry, that linear Dirac cone will transform into a massive particle. And this is the discovery of the hydrogen atom of a topological insulator, bismuth telluride. This was done both the combined experiment at SSRL and advanced light source. And you can see the cone-like shape of the band structure. And this finding stimulated other experiments, eventually led to the discovery of the quantum anomalous Hall in this system. And it is also being selected by the Office of Science as one of the 40 milestones in its 40th anniversary of that. So the other thing is that the program also helped train young people. We all know the importance to have the scientific pipelines and also train. Audie in his talk and Keith in his talk also really emphasized the importance of the workforce development and the importance of graduate student involvement of that. So the ARPAS program as SSRL produced many dozens of university groups, and these are the groups, so the formation groups are now in different universities within the United States. And as I said, start out with Dan Desson, and now the latest one was Yu, who joined the faculty at Yale more recently. We're also very happy that there's 5 group of women who now join the faculty in the physics department, which is very rare in that. So now let me change the topic, talk about the ecosystem. Okay, as Keith alluded to, I think SSRL played a vital role in incubating Stanford interdisciplinary institutes and centers and posts, okay, science and SunCap. Okay, those are the institutes devoted to ultrafast science, material science, and also catalysis. And those inferences are clearly there. And within our own program, of course, we continue want to build an ecosystem where we can basically have synergetic activities, use advanced instrumentation, synthesis, control, and also simulation. So we want to measure basically all the quantum numbers, energy, momentum, space, spin, time. And we want to embed ourselves in this really intellectually rich environment of the university and the laboratory. The facilities represented by LCLS and SSRL, and the laboratory-based pools, unique material synthesis and calculation, also the simulation and calculation. It's very important to have a theory component of that. They enrich the values of the data you collected. This is just one example of how the activities we can leverage and help our experiment at the linear coherent light source. Okay. This was one experiment trying to understand how the atoms and the electrons will interplay on this. In a simple way, many of you heard about electron and phonon interaction. Okay. Now, there are many ways you can measure them. Okay, you can measure them with Raman, optics, but all those experiments require some theoretical input, either density of states or some bare dispersions. And if someone say, I don't agree with your input, then you are in a circle of a debate. The question has always been, is it possible to make an absolute measurement? There's no need for any input. Then you can compare with the microscopic experiment. And LCLS made it possible. The sample is grown by Rob Moore at the SSRL and calculated first at the SSRL. So this is a hard experiment. We want to track the motion of atoms, the movement of energy level of electrons with the precision of basically for atoms, you need somewhere around much better than a picometer, okay? And you need about 50 femtosecond, and you need energy level sensitivity to a few millivolts. Everything needs to be there together. And that's the cartoon, okay, of the data, but the raw data are underneath, and you can see the horizontal scale, the entire scale is more or less 1 picosecond. Okay, you see many cycles, and this is real-time atoms to the left, moving up and down, the electrons following to the right, up and down, and see its energy level shift. Okay, and you can see in the atoms, that's what diffraction gives to you. Okay, you need a picometer sensitivity. Honestly, I didn't thought this kind of experiment was possible, but it is. And allow you to say, we call the terahertz lock-in. As a physicist, we all know the lock-in technique is the one give you the best signal to noise. As a physicist, we also know when you have an idea to make a measurement, everything in the end boils down to signal to noise. Okay, and lock-in give you this. The lock-in technique we do typically in our laboratory are in megahertz or gigahertz regime, which means that you can make a lock-in technique measurement of a macroscopic measurement. This, I believe, is the first experiment pushing into the terahertz regime, and you can do a lock-in experiment on a microscopic quantity. What is the result? The result shows that the classical theory, okay, was off by an order of magnitude. Okay, especially for certain properties, this critical parameter goes in the exponent. Okay, you can see how far off it is when your parameter is. That's kind of technique and power this can do. And to the left, the team who made it possible is a combination of SSRL science and also LCLS. Okay, so that again is the community made this sort of thing possible. Okay, the next thing is also, as Paul alluded to in his earlier talk, about expanding capabilities. For within our own program area of the quantum material, okay, we would like to build on the success of the UV field, and we want to see that we can expand to a different photon energy range. There are multiple reasons. One is because it gives you a different sensitivity. It allows you to make a measurement of devices. And also, of course, that's also the interesting spectral region, certainly in the early days of the LCLS. And again, we want to, when you have a problem that's so difficult, you really have to look the problem in from multiple angles. And I remember when we first find the D-wave superconductor, Phil Anderson, which is a giant in our field, made a comment, said, those who are desperate experiments, because those are desperate problems. Okay, indeed, because the quantum systems are so complex, and you really need to have the most precise measurement to have a possibility to have the quantum projection or quantum shuttling effect. Okay. Now, let me have a few reflections. As I said, Piero's note said, could the source of high intensity X-ray be used to do something novel? He said useful for material chemistry and biology. So I reflect on that. The answer clearly is yes. Okay, what we have learned. One is openness to new ideas. And Pete was, of course, looking at high energy physics. The high energy physics community was building this amazing machine, led to so many revolutionary discoveries. But it was open to the idea in the letter by Bill Spicer, who was stimulated by the visit from Steve Hexton. And that opening was very important. This was 4 years before the sphere ring was built. Okay. The second thing is it built a transformative tool in a science-rich environment. I want to stress the period of 1973 to 75. Okay. In the earlier data, when I presented the first photomation data from Gold 4F, the remarkable results of the early XF data, they all happened in 1974. Okay, remember the high energy physics revolution also happened then. Okay, the so-called November revolution, that was the November of 1974. Okay, that would be, of course, Jay Persai and the Charm Quark, and also 1975 was the discovery of the tau lepton. Okay. So that, of course, led to many Nobel Prizes, started with the one to Bird on the Jay Persai particles. As these the four you can see on the SLAC website. Okay, so that also shows that on day one, the riches of X-ray science, while the high energy physics discovery was made, was very clear. It's going to have a transformative impact on that. Another thing is also very interesting for a synchrotron or X-ray source. It's more of a tool. You look at many problems. We already hear the talk of structural biology, and I hope you hear me talking about quantum materials. You're going to hear Gordon talk about environmental problems, okay, molecular environmental problems. All this was saying you have a tool can look at many things. In many ways, it's quite similar to the building we are in. It's the astronomy. You build a telescope. You look at many different regions of the sky and making different discoveries. It's just the characteristic of this field. And it's so important to build your facility and embed it in a science-rich environment. The last thing, of course, is also obvious, investing in young people and create a pipeline of young talent. I think for all fields, you have to build the futures in young people. It's amazing, Piero, to see your graduate student pictures out there. So it's in a sense that SLAC invested in young people. And as another example, I believe the last speaker, Keith Hutchinson, was the first junior faculty being hired as related with SSRL. I think I'm the second junior faculty being hired related to SSRL. And as I'm participating in many of the junior searches, you are always amazed by the young talent. It's amazing. You want to hire them all, and you can, right? But it's to say that there's so strong incentive to have young talent. That's why in the physics and applied physics department, we push so hard. The dean said that you can only hire 2, we said we want to hire 4. So there's always push for that. And it's so important for any institution to hire young people. So that's what I want to say. And finally, let me say that the future is really bright because this is a facility with a tremendous tradition of innovation and also the involvement of talent. Those are the things so critical for a facility to support, to succeed. And it's such a strong partnership with the university, with the Department of Energy to build resources which can benefit the entire country and the world at large. Thank you very much.